All right, sorry for the online students. The recording cut off, but you didn't miss much. We basically finished talking about molecular bonding in water and fat, and then talked about how fat recovers faster than water. So the T1 recovery and T2 decay times for fat are quicker than water. All right, so here's a good summary of T1 recovery when we're talking about the two different tissues. So remember, fat has a low inherent energy. Think of the sponge. Where it's able to absorb energy into the lattice very easily. Anytime you're giving off energy, you're going to recover a lot faster along the longitudinal axis. Fat has a slower molecular tumbling rate and a lower precessional frequency. So it actually matches up with the Larmor frequency, so there's more efficient energy exchange. So once again, it's giving off energy to the lattice a lot more efficiently and quickly. And then let's talk about water. So water is just the opposite. It has a high inherent energy, so think of the paper towel. Where it's not able to absorb that energy into the lattice as easily. Has a faster tumbling and a faster precessional frequency. So it does not match the Larmor frequency. So when you have two precessional frequencies that are not exactly the same, you're not going to get an efficient exchange of energy. So it recovers a lot slower. So going back to this initial slide right here. Which of these are related to T1 and which are related to T2? What do you think? Inherent energy of the tissue. Which one? T1 or T2? T1, because remember, that's also called what?
Spin-Lattice.
Spin-Lattice, yeah. What about the second one? How closely packed they are?
T2.
T2, good. That's also called what?
Spin.
Spin-spin. How much energy they're giving off to their neighboring nuclei. And then precessional frequency matching.
T1.
T1, good. When there's a better match, there's a more efficient energy exchange, quicker T1 recovery. So very good. So then here, I'm going to give you the actual times that they recover. So in T1 recovery of fat, the net magnetic vector of fat realigns with V sub 0 quickly. So the T1 time of fat is short. So you need to know these for when you take the registry, but also when you're in clinic, when you're typing in T1 values for certain things. So the T1 time fat at 1 Tesla is 200 milliseconds. So you can say here, if this was a 1 Tesla magnet, you basically go up to 63%, because remember, that's when it's considered fully recovered, and then you measure it down here. That's the T1 value of fat, and that would correspond with 200 milliseconds down here. So 200 milliseconds, I would put right under T1 of fat. All right, and then water, or CSF fluid, or any type of fluid, urine within the body, is going to recover or realign with V sub 0 slowly. It's going to take more time for it to realign due to all those properties. So here's a CSF. So it's going to take for T1 at 1 Tesla between 2,000 and 2,500 milliseconds. So we could type down under here CSF, 2,000 to 2,500 milliseconds under CSF. Okay? And you see how that curve takes longer to get to 63%. All right, so let's switch gears. Let's talk about T2 decay. So these things are happening at the same time, but they're independent of each other. T1 relaxation or recovery is happening at the same time T2 is going on, but they're two different processes. So don't always think they're going to recover and decay at the exact same rates. What actually happens is the T2 decay happens a lot faster than the T1 recovery curve, okay? So always say they're two independent processes. They're happening at the same time, but they're two independent processes. So you can't just put the T1 recovery curve on top of this, even though I kind of showed you that on this first slide here. One of these first slides, let's see where it was. Right here. You can't just put this right here and go, oh, well, you can see how fat recovers here, and then fat also decays here at the same time. No. T2 is actually happening a lot faster. So it really kind of looks like this. It decays a lot faster than it recovers. Okay, so that's why they're two independent processes. But they're happening at the exact same time, right as you turn off that RF pulse. That's when both start to change. Okay, you understand that? Okay, so T2 decay occurs when the nuclei exchange energy. Remember, they're giving energy to their neighboring spins. That's why it's called spin-spin relaxation. And the definition of T2 decay is the time when it takes for our net magnetic vector, or our signal, to lose 63% of the transverse magnetization. So 63% of our transverse magnetization has been lost. So a lot of times they draw a line here. They have basically you start off with 100% signal, and then down here 0% signal. So we have 100% up here, and then your signal eventually goes down to 0. But what's 100 minus 63? 37. So a lot of these graphs on T2 decay will have 37%. And that will give us whatever your signal is at 33%. That's basically the time it takes to lose 63% of that transverse magnetization. So you would just draw this out here. Then you drop it down to the time axis. So you can see how your echo time, basically the time for it to decay for fat, is a lot shorter than your echo time for water. T2 decay is unique for each tissue, just like in T1. So here's that curve drawn with 33%. So you remember, what axis is this up here? What plane?
Longitudinal.
Not longitudinal.
Oh, transverse.
Transverse, because remember, once you flip it into the transverse plane, you start with 100% signal. So this is different. So M sub X, Y. So it's good you kind of saw that. Sometimes getting it wrong really helps to hit it home. And then remember, this is time again. So T2 is a characteristic of tissue and is defined as the time that it takes the transverse magnetization to decrease to 37% of its starting value. Or once it's lost, 63%. So remember, on that transverse plane, we're rotating around the axis due to precession. Fat molecules are packed close together. Remember, spin, spin. So they're giving off energy to their neighboring spins, so they dephase quickly. So what's another term that we learned last time for dephase? What do you think? Something phase. Yeah. But D, what would D phase be?
Incoherent.
Incoherent or out of phase. So let's put D phase basically means out of phase. Or incoherent. So we're starting to precess along that precessional path at different moments, right? Remember, we had that precessional path here around B sub 0, but all our little hydrogen protons are not at the same point along that precessional path. So that's what it means to dephase or go out of phase, or those spins are incoherent. All mean the same thing. So fat, since the molecules are closer together, giving off energy, they dephase a lot faster than water. So you can see here, over the same amount of time, those spins have completely gotten out of phase with each other, and then these spins have gotten out of phase, but not as quickly as fat. So water dephases slower than fat. So what does this mean? So T2 time of fat is short, because the loss of transverse magnetization is very rapid. So the T2 decay time for fat is 100 milliseconds at 1 Tesla. So see here. So we got fat, we got different fluids, they decay very fast. Let's talk about water. So that takes usually a little bit longer for it to dephase. So the loss of transverse magnetization is very gradual. So here's just a quick little chart for our T1 and T2 times for fat and water at 1 Tesla, because these are always going to be field strength dependent. So all these times are going to change depending on your field strength. So always make sure you have some kind of field strength associated with these values. And that's because of our Larmor equation. Remember, everything is associated by our static magnetic field. Okay? I think it's 10 o'clock. So we'll stop there and we'll pick that up next time. Any questions? You guys got any questions with what we've learned so far this year?